excited about artificial intelligence, right? And we see it every single day, every time we open up a web browser. A new innovation, a new application of artificial intelligence, right? We have self-driving cars, we have Siri, we have the ability to apply these technologies to so many new problems. And for me, someone that's worked in this field and at FICO for 18 years, it's really fulfilling. It's fulfilling to see, the pedigree that we've been involved in for more than 25 years around machine learning take hold in the larger sort of industry. And in fact, right, if you follow this field, there are something like 2,019 brand new startups in artificial intelligence today. $27 billion worth of venture capital money coming in. So there's a tremendous amount of research going on right now around how to apply artificial intelligence and machine learning to new problems. But despite that, I'm really, really worried and really, really scared. And I want to share some of that with you as we counter and balance all the excitement and all the promise that machine learning and artificial intelligence can deliver to us, along with some of the challenges. So we've heard this, right? Superhuman. And we're not talking about Batman or Superman here. We're talking about the fact that algorithms can perform tasks at a superhuman level. And in fact, the definition of artificial intelligence is it's a technology that performs these cognitive tasks better than the human. As an example, right, if you wanted to get from here, right, to the airport, and you had to pull out a paper map and figure out how to route yourself from the hotel to the airport, right, it would take you some period of time. First of all, you have to locate a map, which was probably still a big challenge, right? But then you have to go through and figure out the route. Now, you compare that to pulling up Google Maps, right, typing in an address, right? That's superhuman. The fact that it can do that in such a way where it can access all the information it needs to, it computes a route, it understands traffic conditions, and within a few seconds, it pops up the itinerary. Now, that's an example of artificial intelligence, and an example of artificial intelligence that's programmed, right? How to figure out the route from here to Miami can be codified. The other aspect of this is machine learning, okay? Machine learning is different than artificial intelligence, and it's important to differentiate the two. Machine learning is algorithms that learn relationships between the data, okay? So it's not a human being that is writing the rules for how this computer program is going to work at a superhuman level. It's the machine or the algorithm that is trying to figure out the right relationships between data. And that is really what is scary in some sense, because it's out of our control. Do we understand what that algorithm is learning? So that brings me to fears, right? And what are we feared about, right? What we have fears about is really around all the promises around AI enlightenment. All the areas that these technologies and these applications are coming into our lives. But before I get to those fears, I want to talk about some of this enlightenment, because many of us have been in this world for some period of time. Artificial intelligence and machine learning is not new to many of you, right? If you look at FICO, right, and I look back on my career, right, we've been doing this a very, very long time. And you see this in our products, right, like Falcon. Falcon was one of the most commercially successful earliest applications of machine learning models. Today, we continue to enhance this, for example, in fraud detection, where we're going to have more than 30% improved detection in card-not-present fraud. You have areas like cybersecurity, one of the largest and most significant problems that faces our organizations, right? Where it is relatively easy to customize an attack on an organization and breach the security of that organization. Money laundering. $2 trillion problem. Less than 1% of money laundering is actually being detected today. It's an area where there's very little analytics being used whatsoever, right? But when you apply machine learning techniques to look for whether or not a customer is behaving like similar customers or not, you're able to have phenomenal detection with very, very little review rates. So great promise there. And even in the areas of credit risk, right? You see when we talk about things like Scorecardizer, right? We talk about the fact that we can go enhance our standard scorecards by training machine learning models and then trying to fit a scorecard to that machine learning model to improve detection while having the advantages of what scorecards bring to us, right? Which are around interpretability and explainability, right? And things that where the regulators understand and we can explain to our governance teams and the regulators how the models work. So we use this all the time, and we're very comfortable with it. But if you go outside of our realm, and you go out on the street, right, most people are worried about artificial intelligence. And, they're worried about this, right? They're worried about the Terminator. They're worried about Skynet and self-awareness, right? Artificial intelligence is not this, and it will not be this, because algorithms are actually very specialized to the problem they're trying to solve, right? But there are legitimate fears that we need to worry about beyond the fact that Skynet will arise and AI will become self-aware. And to give you a splattering of these, here's a couple of examples, right? Killer AI. Right? We have, for the longest time, used artificial intelligence to target weapons. Okay? In fact, parts of FICO in our very early days when we started to, before we pivoted to doing financial fraud, were focused on where should the tank shoot and how should the tank shoot an object because we use image recognition. There's some very, very scary videos out there today about drones, not just drones that we would send to, let's say, attack another country, but drones that your child might play with a little payload on it that could go and target a particular individual using facial recognition, right? Or figure out which ones are the humans and explode near them, right? So it's a scary sort of concept, right? Could this change the way that we do law enforcement or crowd control or something else? AI-powered crime. As I said in the video you watched, right, our adversaries have as much access to machine learning as we do. And in fact, some of the best researchers and scientists are working on the wrong side. And so we have a sort of situation where, whether you like it or not, we have to keep up with machine learning and artificial intelligence because the criminals are not going to have the same sort of constraints in terms of their abilities to apply machine learning to try to work their way around the defenses we set up to protect our customers and our organizations. And we're focused on this. We actually released a patent application around what we call defensible AI. AI and machine learning that leaves little patterns in its responses so that it can make a determination whether it thinks it's being monitored, right? Because machines can learn machines. Bias. We worry about bias all the time when we build models, right? And one of the beautiful things about a scorecard technology is it's a linear additive model. And you can look at each feature and you can make a determination whether or not there's any bias in terms of how a score is produced. You can apply monotonicity requirements, or you can ensure that certain subpopulations are not receiving an adverse sort of behavior or impact. This becomes a really big problem with machine learning because there is this sort of notion that I'll take all the big data that I have and I'll go to all those great open source libraries of machine learning models, and I'll hire a couple data scientists, and they're going to apply the algorithms, and out will come goodness, right? But the challenge is that in that scenario, we very often do not understand what are the relationships that the machine learning model has learned, and which may actually be, in some sense, directly or indirectly biasing different customers. So it becomes very, very difficult because if you use those technologies in a non-cautious way, then bias is a problem where in terms of how customers are treated and ensuring that we are not biasing. And the fourth one, mistaken identity. Today, there are many governments that are having cameras out that are scanning faces across the room and trying to understand identity. And in fact, some of you have phones where you look at the phone and you authenticate yourself, or you put your fingerprint on it, right? Or you say your name and use a voice print. And we're all told or led to believe that these technologies are really, really powerful and very, very highly predictive, right? But there's an entirely new set of technology and research that has demonstrated that if I take that picture there and I change one pixel, just one little pixel, I can entirely change what the machine learning would predict in terms of whether or not that's a human or whether or not that is a particular individual, John Smith. Right? So we need to be tremendously cautious because we get infatuated with the business applications and the promise of AI machine learning, but sometimes we don't think about how easy it is to defeat it or what the ramifications are of how we use it. So what am I worried about? I'm actually more worried and more scared about something than these, right? I'm worried about this. I'm worried about cowboys, all right? And you know, cowboys I'm worried about because they have, in some sense, disregard, right? A disregard for what is proper. They're there to solve a problem. They're going to get it done, right? But what we see today is machine learning being used in a way where very often the data scientists may not have experience with the algorithms they're using. They may not know the limitations of those algorithms. They may be using algorithms that were coded by somebody else, so they don't even know if they're real or implemented properly, right? They may or may not have any notion of bias and regulations, or maybe even a conscience with respect to how they apply these technologies, right? And we as consumers, right, and we as customers, we as a society are going to be impacted by whether or not we're going to have a reckless sort of cowboy behavior with respect to the applications of artificial intelligence, or are we going to have something a bit more measured, something that has a lot more regimented experience in terms of how we develop these models. So, you know, when I think back about, you know, all the excitement, and I think it's a great opportunity, right, with artificial intelligence today, I actually think back to when I started almost 20 years ago. And 20 years ago, you know, we were, at that time, talking about neural network technologies. And FICO as a company actually sold hardware. We were a hardware company back then. We sold what we call snap boards, and some of you may remember these snap boards. So we'd send these boards out to train neural networks, right? Because machines were not fast enough, so we had to create our own computer boards to do it. And we have to explain neural networks to our customers. And we got a grilling back then because it was a relatively new, nascent technology, machine learning, 20 years ago. And we would give an example, and that example generally would be something around a car that would have to hit, you know, when would you have to apply the brake in a car before that car would hit an obstacle? And very often that obstacle was, in the old literature, was a rhino for some reason. And I wanted to modernize that a little bit, right? And this is one of my passions, one of my hobbies. It's car racing. And this is a racetrack in Willow Springs, California. And you can kind of see that it's a racetrack. You have a lot of turns. And you also see that some of these turns are black because that's where everyone left their tires going around these turns. And when I think about machine learning, and maybe it's because of my early time at FICO, I can't separate it from stopping cars. And when I think about car racing, it's all about stopping, and it's all about slowing down, and it's all about turning. So if you're going to get around a racetrack very, very effectively, right, what you want to do is you want to go into this straight as fast as you can. You want to have your foot all the way down on the accelerator. And at the very right moment, you need to know how to switch off the accelerator, slam on the brake really, really hard, brake as efficiently, as quickly as possible, and do it at a particular point, which is called a turn-in point, so you can turn your car at a safe speed and make basically a straight line through that turn, right? Hit one of the apexes, either what we call late apex or early apex, and then as you're through that turn, hit the accelerator again and go as fast as possible, right? And if you do that, that's how you win races, okay? So in this problem, since it is vogue to apply machine learning to self-driving cars, for example, let's apply it to this problem. So how would we solve this problem? One of the things that we know is that machine learning is superhuman. And one of the ways it's superhuman, it gets more experience than any one driver, right? So what we could do is each of you could go take out a car, this car, drive it at different conditions on this racetrack, right? And we would collect a bunch of data. And we don't know what the relationships are between speed and temperature and water on the road and other parameters associated with data we would collect, right? But we'll just go do a bunch of runs. Because we're not going to have to worry about what is the relationship between speed and, let's say, dirt on the road, right? Or temperature of the tires. We're not going to worry about that because the machine learning model is going to do it all for us, right? So we'll just worry about going out, collecting data, and then we're going to apply a machine learning model. One of the classic machine learning models would be this one, right? The one that I've been talking about for 2 decades now. Neural networks, okay? Now, neural networks are powerful for a few reasons. One reason is that they try to understand how to take that data and learn the proper relationships between the inputs that we've gathered. So, for example, speed, the brakes age, road temperature, what have you. And the way this occurs is we just take that historical data of all the drives that we did at different parameters, right? What the stopping distance is, right? And we'll go around and we'll take Stuart, and he did the first run, right? We'll put his data in here, and we'll set all the weights of the neural network to random numbers, meaning that we have not prescribed what the relationships are. And out comes an estimate of stopping distance. We know what the actual stopping distance is. We can calculate what the error was. And that error gets sent back through this neural network where each of the connections, the weights and the importance of each of the features get tweaked a little bit so it can make a slightly better prediction. And then we take the next person record and the next person record, and we iterate this until eventually it gets trained. And it gets trained at the point when it starts to make good predictions of stopping distance. And at that point, we have our model, right? It's seen more data than any one driver would see and has more experience than any one driver could see. And generally, as we saw yesterday also, and we see in our own products, we have very, very strong levels of prediction. But the problem really comes down to this. What did it learn? We often don't know. Neural networks are actually one of the most interpretable machine learning models out there. But what it learns are what's contained in these hidden nodes, because the hidden nodes are the combinations of all those inputs where we come up with the features that are driving the prediction, right? And when we have something called a deep network, we have lots and lots and lots of these hidden nodes. And they capture different parts of dynamics of these features to come up with a better prediction of stopping distance. But did it understand that the car maybe needs some maintenance, right? Did it learn that when it's cold out, like below freezing, and there's water, it turns into ice, and the car takes a much longer time to stop? Well, it didn't learn that in Southern California, right? But we don't know. And that's our challenge here. And maybe we don't care, right? Let's be cowboys. We don't care. We have a great model, right? But I would argue, right, we need to care, right? This is an Uber self-driving car. And as you recall from the news, very shortly after they started it, right, someone died. A pedestrian was struck by a self-driving Uber car. And you read the articles about this, and they say, well, we're baffled, we don't understand, there's nothing wrong with our sensors, right? But they truly just don't understand how or why the car didn't stop. Now, maybe they need people to run in front of cars so it could get trained on the fact that it shouldn't have done that, and it'll make a mistake and have to be retrained. I don't know, right? But this is not the first time that we've had AI kill a person, right? We had the Tesla driver, right? He was sitting there, unfortunately, watching some Disney movies, enjoying the show, and the car swerved underneath the tractor-trailer. Same scenario. They don't know. And so this is a really big problem, particularly if you're going to be in this car, right? Or I'm going to be in this car, right? We need to know how the AI machine learning is making its decisions. And in some sense, right, I like to go back to basics because driving a car, right, with an AI model, that's a very complicated sort of thing to do, right? And we take it for granted. It's something that we're relatively good at. But there's a lot of things that car needs to figure out. So let's make it simpler. Let's just say, well, let's figure out what a stop sign looks like. We're not going to worry about pedestrians. We'll look at stop signs. And so there was a study done, and the study basically said, OK, I'm going to try to understand the very best machine learning model at detecting stop signs. And they had the best humans, and they would have a trial where it was kind of like one of these glaucoma tests, right? You'd have this little clicker, right? And you'd click if you think it was a stop sign, and it would flash up for some period of time, right? And I'm sure there were stop signs that were very, very clear, and there were stop signs that had shadows on them and stickers on them, and they were a little sideways, right? But the best human had 99.22% accuracy, and the machine learning model beat it, because obviously it's superhuman. It could ingest more examples, and it could make better decisions, and it could make them faster. And so why not use that neural network to be a stop sign detector? Well, what was interesting was when machine learning is wrong, it is really wrong. Because when it misclassified a stop sign, it actually thought it was a yield sign. Okay? And us as human beings can go look at those two signs, and very few of us would mistake a yield sign for a stop sign. So researchers basically, well, again, same challenge. How is it making a decision, right? We as humans would interpret, well, it's going to look at the shape of the sign. Or maybe it's going to look at the letters in the sign, right? So for example, right, these are two different shapes of signs. There's an S, a T, and an O, and a P in one of those signs, and there's none of those letters in the other sign, right? That's the way we probably think about this. But maybe the machine learning model is looking for a little bit of white in the center, right? And if it sees that little bit of white in the center of a yield sign and in the center of a stop sign, they're both stop signs to the machine learning model. Because maybe it got more answers right when it made that experiment. And in fact, right, we see this time and time and time again with machine learning, right, which makes it really scary. For example, right, there was another study done around trying to differentiate between wolves and dogs. And they built these models, and they understood that it did pretty well on most dogs, at differentiating dogs and wolves, but it did really poorly on huskies. And they were trying to figure out why does the model not differentiate between wolves and huskies. And it turned out as they did the research, they understood a very scary fact. And that fact was the machine learning model, the biggest predictor, had nothing to do with the husky and nothing to do with the wolf. It only had to do with whether or not snow was in the background of the picture. Okay? So all it was predicting was snow, right? And essentially which animal would be more likely to be seen in snow, right? I don't know about you, but I don't want to be walking in the snow, right? Because it doesn't do a very good job. And we need to think about this. We have to be critical about this, right? And that's one of the things we do at FICO, right? We really put all these analytics through a very extensive examination because these examples are simple ones. But imagine when AI gets very, very complicated, right? Or we don't apply the right sort of governance around it. And it gets harder, right? There are hundreds of algorithms associated with machine learning. Many of them we introduce to you as part of our product and solution suites. Right? There are technologies which are supervised. For example, what we use in our fraud models. Right? We have huge amounts of historical data. We know which transactions are fraud or not. We can train really effective models because we know the outcomes. We have unsupervised analytics, right? Machine learning. Works without tags. Essentially says, I'm not going to have a tag, or maybe my historical data is not going to be applicable to when I want to deploy this model. So I'm just going to look for things that look abnormal. So they focus on what is normal and determining how much abnormal, let's say a record is, or a person is, or a consumer is, from the rest. Semi-supervised. Right? Many of you are familiar with our adaptive technologies. Right? This is where models work directly with the human analysts. There's a sort of very tight integration where analysts are getting presented cases by the machine learning model, and the machine learning model is learning continuously from that interaction with the human analysts. And the fourth flavor here, deep learning. Okay? And I'm generally not a huge fan of deep learning because it makes it much, much more difficult to explain what the model does. But deep learning has a lot of advantages when it comes to understanding shifts in data, right? And so we'll talk more about that. Now, we are in a new age, and AI and machine learning is not going anywhere, okay? And Same way that cybersecurity was a nation-state issue, right? AI and machine learning is going to be a nation-state issue, right? So we're going to have governments using artificial intelligence against other governments. We're going to have businesses trying to differentiate from each other with artificial intelligence, right? And then we have the challenge that we often don't know how the technologies work. And so a big part of where we need to get to responsibly leverage these artificial intelligence and machine learning techniques is around making AI explainable. And fortunately, right, we at FICO spend a lot of time on that. The scorecards that we develop, right, tremendously powerful from an explanatory perspective, right? These are additive models where you have features, where each feature is some nonlinear relationship of a weight of evidence of, let's say, delinquency. And you can go count up, you can compute a score by adding up points associated with each of these features. And then when it's time to say, what are the reasons I didn't get the very best FICO score, right? You can go across all those features and figure out where you lost the most points. Very, very easy to explain, very much accepted today. But there's other sort of techniques out there. And FICO has been a pioneer in this space. We actually have 2 algorithms that have already expired, meaning that they're more than 20 years old in terms of our thoughts around how to explain machine learning and neural network models. But I'll give you 4 flavors of this, so you have some notion of where the research is headed, and you have more awareness as you try to, let's say, bring that machine learning technologies to your businesses. First is called local perturbation. Essentially, you score with the machine learning model a customer. You have the values of the variables, and you're basically changing the variables very, very slightly to see if it has an impact, right? So let's say I have a Falcon score of 960. It might be very likely fraud. The country is Kazakhstan. I switched to Kazakhstan to the UK. Did the score change, yes or no? And how much did it change? If it didn't change very much, country is not something that it's sensitive to. There's something else driving the score to 960. And so these are iterative approaches that perturbate the record to try to figure out what's driving that score. We have interpretable architectures, okay? This is a situation where we basically say, I'm not going to go through the friction of trying to explain machine learning to my supervisor or to my model governance team or to the regulators, right? I'm going to go and fit a model that I already know how to explain to a machine learning model. So a great example of this is Scorecardizer, where we have a machine learning model that we've built. We try to fit with a scorecard what that output of that model is, so that we can take advantages of a decent amount of the lift that machine learning would give us, but have all the explainability that we would have with these scorecard technologies. For those of you that use Falcon, there's global-based methods. These are basically methods that look at the data on which the model was built, and it says, for a particular value of a feature or a variable, what is the most likely score that would be produced? And we associate reasons with the most likely values of different variables, whether they be on the input layers of neural networks or on the hidden layers, to associate reasons. Okay? And the very last is new research around coming up with machine learning that is focused on exposing latent features. Essentially coming up with new architectures that put explainability first and prediction second, right? For 20 years, we've been dealing with the fact that the models that we build, for example, neural network models, are black box, right? This research is around making these models more interpretable and making that a focus from the onset. Because ultimately, we're going to have a conversation, right? And that conversation is going to be with our model governance teams, right? It's going to be with our regulators. It's going to be with our customers. And you're seeing it all the time now, right? We have GDPR. GDPR states that if you're going to use a machine learning model, right, to make an automated decision, you need to produce reasons, right? And you're going to be able to have to stand up and have a very plausible way to be able to say, yes, I can explain what these reasons are, and this is what the algorithm looks like. And everyone has to be able to understand that and believe that, right? And you have to be able to have the conversation with the customer in such a way where you aren't going to say, the machine learning model told me so, right? The customer is going to expect that you speak to them in a language and a terminology that they can understand. How do I improve that score, or why did I get that score? So this is actually a really big part of what we're facing today. In some parts of the globe, they're saying, well, we're going to hold off on machine learning, right? We don't know how to solve the explainability issues, right? And maybe it's too difficult to get there with the regulators, right? In other parts, they're going to test this out. So the next 3 to 5 years is going to be interesting in terms of how machine learning gets adopted from a regulatory perspective. Where does it pass? Which algorithms will work best, right? And that will kind of be the ones that are going to be testing the waters of what's considered acceptable in the use of machine learning. So we prevent some of those challenges with respect to, the snow being the predictor for wolves. Now, part of this is what we're used to, right? And coming back down to basics. And this is part of why I'm so scared. We don't even have these conversations very often, right? Someone presents you a machine learning model, right? 20 years ago, you would explain, what is the data I'm building it on? How many epochs did you train my model? What's your test train split? Can you demonstrate to me the data exactly will be like what I do in the future? Today, I think we've become so accustomed to these technologies that we forget that they're very dangerous, right, in the hands of somebody that doesn't know how to use them properly. And so data governance. What is the data that we're going to use to build this model? Do we have permissible rights to this? Is the data going to be similar to what we're going to apply in the production environment? When we took the car out and we selected all that data around stopping distances, right, that model worked well in Southern California. It's not going to work at all in Canada, particularly when it's cold, right, because it didn't learn ice. And so we need to go look at what the data was that we used to build the model and is applicable to our customers and is applicable across the regions or areas of our business. Model governance is going to become even more important, that we look at each and every feature, that we ask questions of our data scientists, right? These cowboys exist everywhere. They exist in my team, right? When I onboard fresh PhDs, many of them focus on showing me a great performance curve, but they don't think about whether the model's robust, have they selected that properly. And that's why we have model governance for the entire modeling process that we have. In fact, if any of you are interested, I'm actually starting to use blockchain to monitor our entire model development process, right? So it's auditable, and I have some level of confidence that we've gone through that. But once that gets released and it passes through governance, right, there's more. There's data monitoring and model monitoring. Data monitoring is going to become more and more important to us. We need to be monitoring these models continuously. We don't want to be the Uber, right, that hits the pedestrian in our businesses. We need to monitor the data. We need to understand when that data is shifting and how it's different from what the model was developed on. And with model monitoring, it's the same. We need to understand and look at these models very critically in real time to understand how the model is deviating from what we would expect. When do we have to interject because maybe the environment's changed so much that the AI model may not be applicable anymore? And if you're interested in that, Matt Cross from Tesco and I are going to give you a very interesting example of that with respect to how reason codes drive some of the changes in explanation. So we're facing a world that is scary. We have a stampede of machine learning and artificial intelligence coming to us. We have $27 billion in venture capital poured into new applications of artificial intelligence. We may or may not have good governance around how all these are developed, right? So it is a scary thing, particularly as it's going to start to impact us, not just in the businesses that we have here, right, but the businesses we have outside in our normal lives. And it's not going to be the cowboys that are going to help us. In fact, some of the cowboys are going to create these issues, right? And we're going to have to step back and talk about regulation or governance, right, as we see AI make mistakes. But it's really going to be around governance, right, and regulation. And with that, we're going to be able to have a more responsible use of AI and meet all the promises that we will have with machine learning. It is an exciting time, right? But we need to do this with great caution, right? Because in the wrong hands, AI can be tremendously damaging in addition to being tremendously valuable to our businesses. Thank you.